All right, back here. Um, Interference 39. Um, where's my paper? So basically, when you have interference with films, well, you cannot. I mean, there are two things you must remember. One is the film itself is supposed to be something very thin with respect to the other surface. And basically, you have two regions of reflection. You have the first region, right, which is the top part of the film, and you have a second region of reflection. That's the first thing. And then you're looking down from here. Now, that's the first thing. The second thing is that the amplitude of the electric field coming out of this reflective light depends on this subtraction here. I mean, the direction of the electric field depends on this subtraction. So if N1, the index of refraction of the medium the light is going through, this is N1 and this is N2. So the slide ray is being reflected from N1 and from N2. Now, if N1 is less than N2, right, then the electric field will have a direction that opposes that of E1, is 180 off. Then flips. It's a pi. If this is not the case, oops, sorry. Uh, so let's see, N1 is bigger than N2, then no flip. Okay, that's the thing we have to remember. Oops. So let's do let's do the 39. Okay, so we have a subbubble. Oh, that's the second thing you must remember is when you punch any wavelength, this is the wavelength of light. Is the wavelength of light in the film, which means if lambda air is given, the lambda to be used is lambda in the air divided by the index of refraction of the film. Okay, so we have a subbubble, the thickness is given. Thickness illuminated by a white light incident. So white light, you have all the possible wavelengths, right? So we have red, blue, violet, and so on, so on, so on. That's why it's white. But when they go and they pass through the film, there will be constructive interference, and some of this constructive interference will be highlighted. So that's the idea. That's why we see different colors, because some of the colors they destroy themselves, some of the colors add themselves. Okay, so we have a thickness that is given by this, illuminated by white light, perpendicular to its surface. What wavelength and colors of visible light is most constructively reflected, assuming the same index of refraction as water. Okay, so index of refraction is 1.33. And then, what is going on? Just get out. So you have your film. That's your film. So white light goes in there. So the optic path is T plus T is 2T, right? It's 2 times this because you have the optical path is down and up. So if you want a constructive interference, we wanna these lights to add up. The question is the index of refraction of the first light ray, the one reflect off the top, is the one that is being reflected from air to water, and this guy is gonna flip. So the light ray that's reflect from the very top does not flip. Then, so you want a 2D or 2T, 2 times the thickness, which is the optical path, to be equal to an integer number of wavelength, right? Integer number of wavelengths. Why is that? Well, because it flipped on the first, but not in the second. Okay. Because why? Because it's a soap bubble. So this is air. So better saying that should be better doing like this. This is air. So which means in the second you have light ray that comes from index of refraction 1.33 and goes back to index of refraction 1. So it does not flip, right? It is already flipped. Does that make sense? So the light ray that goes through the refracted light ray, refracted, does not flip. So we start, with the electric field in a given direction, refracts with the electric field being the same direction. And since it now reflects off the inner part of the air bubble, it does not flip when it reflects. So it's still 0. And then this should be true. Now, the main situation now is that the lambda should be the lambda in the air divided by the index of refraction. Don't forget that. And then we can find the wavelength. So the wavelength should be equal to, so we wanted the first one, m equals 0. So it's 2 times 2 times 1.33 times t. Okay. 40. An oil slick on water. So now we have oil. So oil has an index of refraction 1.4. This is water, right? Index of refraction is 1.33, and you have the white light going that way. The thickness is given, 120 nanometers. And now, the first reflected, it comes from air, n equal 1, and go to oil n equal 4. So smaller to the biggest, then you have a reflection here that is going to pi, is going to change. But now you are in an index of refraction 1.4, right? You enter this light ray is, it does not flip, right? Does not flip. So let's say if it goes 0 here as an incident light ray, it's still 0. It's still with the electric field in the same direction when it hits the water. But now it goes from 1.4, which is the film, to 1.3, and therefore does not flip. So it comes out not flipping, which means to have constructive interference, we have to have a integer number of wavelengths, the pathways. So 2t must be equal to n plus half lambda, the same idea. Okay, and basically we do the same. We place n as we did in the previous problem. We make n equal 0. Lambda is should be air divided by the index of refraction of the film itself, and then we can find what do we want to find? Well, we want to find the wavelength, and then we can determine the wavelength because t is given. Let's see, number 41. It's the same thing, right? Number 42. 42 is the same, except the unknown is the thickness. So yeah, it should be the same. And 51, Michelson, don't worry about it. So in this chapter, thin film interference, so focus on that. I also would like to go over we did this in class, and we didn't finish. And I was revisiting this just to make sure I cover all the possible parts. We didn't work so much. I mean, this is a nice problem, and I don't know why it's a clicker question because it seems to be kind of a demanding. Oh, we didn't do this. It would be nice to do this one too. Okay, so let's take a look at this problem here. You have two radio antennas. This is basically a double slit, right? Double slit. You have two radio antennas. They are in phase, so we're pretty much coherent, located at point A and B, and they are separated 6 wavelengths apart. Radio receivers moved along a line from point B to point C. There you go. At what distance from point B will the receiver detect an intensity maximum? So how do we figure that? So we have these two radio sources. They are separated by 6 wavelengths. Point A, point B, point C, right? So we want to find which point you have a maximum intensity. So this is R1. This is R2, right? So to be a maximum here, you want to del R, which is R1 minus R2, to be equal to an integer number of wavelength. What else? What else is given? So this is move along this direction. This angle here, therefore, is 90 degrees. And we want to find R2 to make maximum. Now that's complicated. Wait a second, how do we do this? We know 6 lambda square plus R2 square is equal R1 square, right? Oops, what did I do? Okay, but R1 is equal R2 plus m lambda. So I can write 36 lambda square, you know what I'm going, plus R2 square is equal R1 square, which is R2 square plus m2 lambda 2 plus 2 m lambda R2. This can be cancelled. And then we have 36 lambda square is equal m square lambda square plus 2 m lambda R2. Cut lambda, cut lambda, cut lambda. So then we can find R2 is equal 36 factor lambda, then multiply 36 minus m square, right, divided by 2m. So R2 must be a positive number. Now you can do your analysis. So R2 is not a negative number, so m is an integer, right? So can we put m equals 0? If we put m equals 0, it does not satisfy. So if you put m equal 1, put m equal 1, we have R2 is equal lambda. 36 minus 1 squared is 35, divided by 2. That is 17, oh no, 17.5 lambda, is that correct? Yeah. How about for m equal 2? For m equal 2, it's possible. So we have 36 minus 4, right? It's 32 divided by 4. So we have basic lambda. For m equal 2, we have R2. The second position is lambda. Then multiply 36 minus 4, 32. Divided by 4, which is a lambda. Now for m equal 3, we have 36 minus 9. So we find R2 is equal 9, 36 minus 9. What does it mean? 27, right? Lambda 27 divided by 6. And then you keep doing this thing. So you go for m equal 4 up to m equal 6, right? M equals 6, you put R2 equals 0. And which means you are at point B, which is a point of maximum. So what are the answers? So B is a possibility. Didn't we get B? Oh, yeah, we didn't do. Yeah. So which for 4.5 that would be what? 4.5 is which lambda, which n equal 4? Yeah, 36 for n equal 4. R2 is equal. R2 is equal lambda multiplied 36 minus 16 divided by 8, right? So that's 20 divided by 8. 2.5. Is that what we had? 2.5? 4.5? Did I get 4.2.5? 4.5? I don't know if I get 4.5. Anyway, so just go doing the analysis. Okay. All right. This is pretty much chapter 3.